So, yeah, thanks a lot for having me, and thanks a lot for staying here for the very last talk at a sunny evening. Yeah, my day today is the whole day concerned with matters of women in computer science. I started my day with a seminar course about gender aspects in computer science, which I teach every summer. Then I had a meeting with the European Cost Action Network about gender equality in informatics, where we prepare some European joint actions to promote women in computer science. Afterwards, I had a meeting with a journalist from Vienna, because next week is Girls' Day, as you might know, and there I have been virtually invited to Vienna for a panel discussion. But now, today, I'm here to talk to you at the Women in Data Science conference about the third wave of artificial intelligence, from black box machine learning to explanation-based cooperation. Yeah, so when I saw some faces of you and looked of the names, some of you I know, I think, I assume that I'm among the elders in this audience. Indeed, I studied computer science in the 80s, and I did my habilitation in computer science in methods of AI group end of the 90s at TU Berlin. So what you see here is a very short history. So I assume that by now everybody knows about the history of AI. This has been different some years ago when the hype started. One had the impression that most people talking about AI were not aware about the long research tradition AI has. So as I assume you know lots of the history, I just want to motivate the title of my talk with this slide, which is called The Third Wave. Typically, the first wave of AI is characterized by technology methods for knowledge-based systems. So in the 80s, researchers developed very powerful inference mechanisms, representation languages for expert systems. Declarative programming was researched extensively. Like now, specific hardware has been built. In this time, it has been special hardware for Lisp interpreters, for instance. So you also might know that an AI winter started, the second AI winter, due to the knowledge engineering bottleneck. In this time, researchers hyped one technology, knowledge-based AI, right? As now another perspective is hyped, machine learning. So in this time, researchers tried to solve all problems by explicit modeling of knowledge. Obviously, this is doomed to fail, because human knowledge has not only explicit, but lots of implicit components, which are really hard to grasp and really hard to formalize by explicit rules or other knowledge structures. So because this exclusive focus on knowledge-based systems, the second winter started, and machine learning, which has been around since the beginning of AI in the 1960s, machine learning started to become more and more prominent. When you want to do a little bit historical research, I recommend to look at the proceedings of the ICHCAI, the most well-known general AI conference, which is not specialized to one specific subject. And there you can see the number of papers dedicated to specific fields like knowledge-based or machine learning. So machine learning was around the whole time. Decision trees and other approaches, neural networks, classic neural networks are rather old, but end of the 90s, SVMs developed. People looked over the time more or less often to Bayesian learning and so on. Yeah, so this second wave is called categorize. Here, statistical learning has been the dominant area of research of AI. And then with the big bang of deep learning, people now become more and more aware that if you don't have contextual adaptation and the ability to explain what black box classifiers are doing, maybe the next winter is coming faster than we think it now. Okay, so 2019 in summer, pre-corona, I was in London and met Stuart Russell, who is one of the authors of the famous AI textbook, AI: A Modern Approach, the Russell Norvig, very recommended. And he said in his talk, we, the AI researchers, never asked ourselves, what if it really works? And this is completely true. Before this hype, my whole life as a researcher has been focused on basic research, comparing one approach against the other, but never looking really at applications. Yeah. So for a long time, there was no Kaggle. Everything was the machine learning repository, which you might also know when you, for instance, look in machine learning. And there are some practical data sets admitted, but many of them are, yeah, I think not so interesting for real world problems. Okay. So now when AI came from the lab into the real world, of course, we need to ask ourselves, who can comprehend and control decisions of an AI system, typically a learned model, very often a deep learned model, if it learns and acts autonomously. The learning autonomously is with restriction because typically we look at offline learning systems. But in general, I think this is the question we are asking ourselves now. Yeah, since we are have already had today a special session on deep learning, I also assume that many of you are experts in this domain. Nevertheless, for those who aren't, I shortly tell you what, in my opinion, and I think many people would agree, was one of the main reasons for the current hype, or the now already 2 or 3 years ongoing hype about deep learning. I think the big thing was when 2012 at the ImageNet challenge, the first time machine learned approach was the winner. Before that, it was basically classical computer vision methods which were successful here. And when you look at the classification error decline from 2011 to 2012, you see here a significant decrease. Yeah, which is due to the very good performance of AlexNet, where doctoral candidates in my group would say, well, this is a really small network, yeah, AlexNet. But in 2012, this was a sensation and really a deep network. So what we had here for the first time is we saw in a practical application that it is possible to have end-to-end learning. meaning that we learn directly from raw data, in this case from bitmaps, from images, without the need of previous feature extraction. So basically, this is what interested then lots of people in application domains in industry. This looked like you don't need to think, you just sample data, yeah? Replace thinking, replace hard hands-on engineering and handcrafting and thinking about domain knowledge and so on, which we also heard a little bit in the last talk, which I liked very much. We don't need to have all these expensive engineers and computer scientists anymore in our companies. We replace thinking by sampling data. Yeah. Okay, but of course, that's not how it works. When we only focus on purely data-driven machine learning, we have several problems. A first problem is data quality. In many domains, there are not enough data available to train deep learning models in the intended manner. We heard a talk by Maya, 2 talks before this one, about small data sets and transfer learning. And we heard about data augmentation, but in general, there might be domains where we really have not enough data and where data augmentation is dangerous because we might have unwanted biases in this way. So another problem with data quality is that supervised machine learning presupposes that data are labeled, annotated with ground truth. For general categories like animals or traffic signs, like we see it, for instance, in ImageNet and other data sets, this can be done with a crowdsourcing with a suitable reliability. But what do we do in medical diagnostics? What do we do in quality control in production? Think about the cost involved if human experts in medicine or in engineering in production would have to label many data sets. So labeling can definitely be as expensive as knowledge engineering in the general case when you have high demands on reliability and validity of the labels. Furthermore, the distribution of data in the training set should be similar to the true distribution, but many machine learning approaches are sensitive to imbalanced data and result in sampling biases and unfair models. Thus, imbalanced data we have, for instance, in medical diagnostics, when, for instance, a really dangerous illness occurs very seldomly in contrast to other illnesses or healthy cases. Same in quality control, hopefully waste parts which are not accepted and not acceptable should be a very low percentage. Yeah, so in general, we should be aware, and of course, you all are machine learning experts, so you know this already, that there is no bias-free learning. We already heard about the no free lunch theorem, which initially has been introduced to show that learning cannot happen without an induction bias. And neither machines nor humans can learn without a bias. We humans sometimes get a demonstration of these biases when we eagerly generalize and we overgeneralize in an undue manner, resulting in stereotypical categories and prejudice, which is basically the downside, in my opinion, of humans' fantastic capability of generalization learning. In contrast to most machine learning approaches, we humans are mainly and often capable of metacognition. So we have the chance to be aware of our stereotypes and prejudices, yeah, and we can counterbalance them with knowledge-based conscious processes. In general, this you also know, learned models can never be error-free. And even if it sounds really good, 99% predictive accuracy, we need to be aware that such a model commits an error for 1 in 100 cases, a miss or a false alarm. Yeah. So we talked a little bit about autonomous driving in this session or the session before. And obviously, 1 error in 100 driving situations is nothing which we want to see on the road, I guess. Yeah, so very often when we train when we train machine learning models, there might be the case that our sampling, data sample is biased in such a way that we get an overfitting to some unwanted features in our data. And this has been shown very nicely in a paper by Sebastian Lapuschkin and colleagues from the Heinrich Hertz Institute in Berlin in the context of their approach LRP, layer-wise relevance propagation, where she could show, where they could show that when you think your classifier has a high accuracy because it classifies a horse as a horse, you might be, this might be not really the case because the classifier, for instance, has focused on some completely irrelevant information, like here the text at the bottom, left bottom of the images. So if such a text is there, your classifier says there is a horse, and if it's not there, it doesn't recognize a horse. Yeah, so there are means to unmask such overfitting, such clever Hans predictors. Yeah. I think if we are not really careful, the next AI winter will be here sooner rather than later, and it will be due to a data engineering bottleneck. Remember, the second AI winter has been triggered by the knowledge engineering bottleneck. Yeah. Okay. So what can we do to avoid this? Because AI winters mean that when you say you are an AI researcher, people say, well, you really do AI, this never worked. It's really hard to get funding and there are not much positions around, right? This is when an AI winter happens. Yeah, so we want to avoid that. And here, one suggestion I have is try to be a little bit more ambitious to look at what can we learn from human learning. So I already told that learning has implicit and explicit components. Learning is typically or not batch and not static, but human learning is lifelong learning. It's incremental, it's correctable. Humans very often can learn from few examples. And another point is when we already know something, by being told or having learned it before, we don't need to learn it again. Yeah. So hybrid approaches should be researched and applied much more than this is the case currently. Combine learning and reasoning. So I want to advertise a conference I'm a co-organizer of in October, International Joint Conference on Learning and Reasoning. So we humans can learn from few examples, very complex categories and concepts. You know this when you have experience with young children, that, for instance, they overgeneralize regular forms, for instance, past tense form of verbs. Yeah, they might say gegangt, yeah, instead of gegangen, because they overgeneralize the observed regularities. This is really impressive, how fast children learn grammatically grammar rules. And another case, another example where you can see this is what I have here at the bottom of the slide. This is from Josh Tenenbaum, a very famous cognitive scientist at MIT. Imagine that divers in deep sea have found new species, and so these three where we have the red squares around them, we call tufa. Now everybody listening now, yeah, would agree that the top left object is also a tufa. They are all different, you see that, right? But nevertheless, the family resemblance is strong, so this is a tufa. And what is below this one is not a tufa. We learned this from 3 instances. Problem 2. With purely data-driven machine learning. The first has been data quality. The second now is comprehensibility, transparency, and control. So at least the developers, the people training, the experts training neural networks, training models, should be able to look in the black box. They should be able to recognize overfitting. There I already gave you an example. They should also be able to evaluate functional safety. Greetings to Gesina, who is in the audience. But we have not only the developers as stakeholders, but also people interested in the content matter of the learned classifier, the learned model. There are domain experts like medical doctors, quality engineers, who must be able to understand system decisions. From what inference, from what information, what inference have been drawn, and they must be able to override and correct system decisions. Who is the master? Who is the slave in this scenario, in this socio-technical system? It should be the domain expert and not the trained model, right? So the domain expert should have the right to override the model, maybe not in real-time situations like when you need to avoid a dangerous obstacle or something, but for instance, in medical decision-making or quality control, this is definitely the case. Furthermore, the right to transparency should be possible to be implemented in a broad area of applications, finance, marketing, health, for end users. This does not mean that companies have to tell the end users and their rival companies about their algorithms, yeah. But for instance, when you don't get a loan, or when your insurance gets very high, you should have the right to get, for instance, a counterfactual explanation, which tells you, well, if you would be 5 years younger, you would have got the loan, or well, if you would earn 10,000 euro more per year, you would have gotten the loan. This is nothing which gives away secrets of an algorithm, but it nevertheless explains the end user why he or she did not receive something, or did receive something like unwanted advertisements. So we still are at problem 2, comprehensibility, transparency, and control for different stakeholders, the DevOps, the domain experts, the end users. And in general, comprehensibility, meaning understandability, explainability, should be given at least for critical domains, is my opinion, is the opinion of many researchers in AI. And this is what we mean with third wave XAI, explainable AI, which is also rather fashionable since the last 2 years. But sometimes now you read stuff like, well, we highlight visually the information which is used by our classifier, so it's explained, so people are now trustful, and now we can apply the system. Yeah, this is a little bit naive. First, you can have wrong explanations and you can have unjustified trust. And it is really a very challenging problem for interdisciplinary research to come up with methods for explainable and interactive machine learning, which helps to keep the humans in the loop and which helps to give explanations which relate really to the model and which can inspire trust, but which can also monitor whether a human starts to have unjustified trust. Yeah, this would be really interesting. So I'm interested in combining explainable artificial intelligence with interactive learning to keep humans in the loop. And I think what we want in our future society is an enhancement and not a decrease of human competence, of human competence. And we sometimes also need human feedback to learn from their corrections of system decisions. Yeah, very often we hear, well, there is this trade-off between interpretability and accuracy, and this cannot be resolved. So if you want to have high accuracy, you need to have neural networks, maybe deep neural networks. And if you want to have high interpretability, you go to linear regression and decision trees, but basically these are crap because they have not a high accuracy. Yeah, and this is simply not true in this absolute formulation. So I strongly recommend the paper by Cynthia Rudin, Stop Explaining Black Box Machine Learning Models for High Stakes Decision and Use Interpretable Models instead. For many domains, we have tabular data, yeah, we have features, yeah. When you look in practice, in applications, in companies, then you have not so many applications where you really need to learn from images or sound waves or sensor measurements, time series. There are these domains, but many domains rely on tabular data, and there, classical interpretable approaches to machine learning are very robust and perform really good. Some years before this, there have been a paper, do we really need hundreds of classifiers? And there was an extensive study with many data sets. And in the end, mostly random forests were superior to all other approaches like SVMs and neural networks. Yeah, explainable machine learning. With this slide, David Gunning started the hype. This has been at ICHKAI 2016. And when you look at this slide shown by David Gunning from DARPA, you see the following. He said, well, currently a machine learning system tells you this is a cat and this is all you get. But what you want to know is that you want to have the reasons why the system thinks this is a cat. And what you see in this green square is that David Gunning, 2016, already had in mind that we have multimodal explanations. Yeah, this is not a highlighting in the image as an explanation. What you see here is a verbal statement stating features this is a cat because it has fur, it has whiskers and claws. And then you see prototypical explanations by showing images of typical ears of cats, because this is hard to verbalize. And this is kind of how humans would explain something, yeah? Yeah, since this time, many approaches have been developed. IBM came up with an AI explainability 360 toolkit, where you have several types of modes of explanation generation, case-based reasoning, feature-based explanations, which is here contrastive examples indeed, and many others. Like Andrea in the talk before me, I also came up with my own little taxonomy to help me through the jungle of explainability. And so I separate interpretable models and post-hoc explanations. So what we already saw was LRP. This has been this highlighting, which is a model-specific post-hoc explanation. Another one everybody knows now, I think, is LIME, which is a model agnostic post hoc explanation. Model agnostic means you don't have to touch your learned model. You keep it as a black box and you do something around it, which I will show you. And on the other side, when you have interpretable models, intrinsically transparent models, like a random forest decision tree and so on, or what we are doing in my group, inductive logic programming, you have in principle explainability there, like with standard software in a way. But of course, these models might be very complex. So nevertheless, you need techniques, methods to generate explanations out of these models. So when you want to explain something, there are different possibilities. You can explain verbally, on different degrees of detail. You can explain visually, maybe with symbolic annotations. You can give prototypically examples, and you can give contrastive near-miss examples. In general, there is no one-size-fits-all. What explanation conveys the right information for in a given situation with a given goal to a specific person is different, is dependable, depends on context. So explanations are not always helpful. In a recent paper with Muggleton at the Machine Learning Journal, which has now appeared in March, we show that explanations are not always helpful. So explanations can indeed be harmful. And one reason why an explanation might be harmful is because the explanation might be cognitively more complex than what is to be explained, right? And this is what we looked at in this paper. But of course, there are other ways in which an explanation can be harmful, for instance, because it might lead to unjustified trust. Maybe the explanation is simply has not related to what the model is really doing. So I think I have another 10 minutes, and I assume that you know about LIME. If not, I apologize, and I can go back to the slides and explain it in the discussion session. I just want to make one point here. So LIME, maybe let's go back to the slide. What LIME is based on the idea of perturbed samples. So structuring an image into superpixels, into clusters of pixels with high similarity, and then putting parts of these superpixels on and off. Giving these again as input in the classifier and looking when the class decision stays the same and when it changes. And Ribeiro showed in this paper that this works really quite nice for these typical images like we see here, like this tree frog, or he showed it with a dog and a husky and a wolf. I had a student who applied Lime to a very different kind of images. We also had in a talk before heard this is like microscopic images, in this case of malaria infected cells. The original method used in Lime, QuickShift, shows you really not the relevant information. Why do you think this cell is infected? In contrast, Compact Watershed exactly finds the relevant part. So what we see here is, please do not simply use approaches from the shelf. Yeah, you can change the superpixel method for Lime, and you should adapt what you use here to the type of images you are looking at. Another point I want to make is that the hype about visual explanations maybe is a little bit too high or too big. When you want to understand why you see here pain in contrast to happiness in a face, for instance, or why your model classifies some image as waste in quality control, yeah, it will not really help you to have highlighting, yeah. Highlighting only shows you the obvious, that emotions you can rather find when you look at the eyes of a person and not so much when you look at the chin or the earlobes, yeah. This is not really conveying interesting information. What you need when you have these complex expert domains like emotions, like medical diagnostics, like quality control, you need a much more expressive language for your explanations, which is able to express spatial relations. This is a waste part because the blowhole is on a supporting part. Yeah, a highlight just highlights the blowhole, but this is not enough, because if the blowhole might be on a very on a not supporting part, this might be irrelevant. A quantification, this is not waste because all blowholes are smaller than 1 millimeter in diameter. Or features, the eyes are shut and not open, so this is more pain. Open would be startle or surprise. Or a negation, there is not a blowhole, but a hairline crack, or even recursion. An arbitrary number of objects of increasing size is relevant to classify this gravesite as belonging to Iron Age. Yeah, so what I'm advocating is looking at these more complex explanations and generate them and combine this with interactive learning for human AI partnerships. Of course, there are domains where we want to have autonomous systems where the AI system decides. And there are domains where it's really good that the assistant system only gives information and the human decides. But there might be many, many domains in complex decision situations where a human AI partnership really would help to support complex decision making in a better way than when you would let it do a human alone or an AI system alone. Here is one example. In a BMBF project called TrameExco at Fraunhofer, we look at explainable and interactive machine learning for medical diagnosis. And what you see here is a simple prototype which has been realized by my doctoral student, Bettina Finzel. You see here a tissue, a microscopic image of a tissue, and you see that it has been classified as belonging to some tumor class PT3. And now you, as an expert, of course, this is still a prototype. This is not a user interface you really would give to a doctor. Yeah, this is still in the lab. Yeah, you can say, well, why does my model decide that this is PT3? And what you see here is a rule. This is prologue. We do a lot of prologue in my group, and a verbal explanation, a verbalization of the rule. And basically, in general, now the expert can say, here is a part which is not, which is not how an expert would diagnose this, and he or she can mark parts of the explanation and change them, and can, for instance, say this part must not occur in the explanation. And when you then adapt your model, you have this information as a constraint. Of course, you might say, well, what are you doing with learning prologue programs for an image domain? Of course, we collaborate with another group in this project, which does deep learning. And basically what we exploit is that you can have deep learning models which detect different types of tissue here and the regions, and then we can use these as an input, as an already interpreted input to this higher level symbolical machine learning. So we do similar things in the context of analyzing facial expressions of pain. And here we use, for instance, contrastive explanations. Imagine you are in a nursery home, and there is a new nurse there. And there is a new nurse there, and the nurse thinks that Mrs. Huber don't like the food currently, and thinks, well, let's put the food away. This is disgusting to Mrs. Huber. But in reality, Mrs. Huber experienced pain, and the difference you can show when you contrast an image of Mrs. Huber when she is disgusted in contrast to pain. Okay, now we have a big issue in privacy of data. Of course, we want not that humans' faces are permanently monitored by cameras. Think about this in a hospital or in a nursing home. What we plan to do when this would be put in practice is to project the image, the information in the image on an avatar face for these type of explanations, so that the images never must leave the camera. A last example, Dare to Del. There we use interactive learning to learn which files might be irrelevant and can be deleted. This topic was very of much interest to many companies. When there has been a report in a newspaper about this, afterwards many people contacted me, and we even made it to the Bild print. Yeah, software made in Franconia supports data messes. Yeah, okay. So I'm coming to the end of this talk, and I want to wrap up. Many application domains have requirements which cannot be met by data-intensive black box approaches alone. Interpretable machine learning approaches, such as regression, decision tree learning, or inductive logic programming, are less data-intensive and inherently transparent. So I think it's a good way to go to combine deep learning and interpretable approaches to learn classifiers for image data together with relational explanations. An example I gave you with the blowholes and so on. And I strongly believe that mutual explanations and interactive learning allow to integrate expert common sense knowledge into the learning process, which we are really in need of, I think, resulting in approaches where we need less data and we allow to correct erroneous decisions of the learned model. And if you want to learn more about explainable AI, I recommend our online course at KI Campus. Thanks a lot.